Hi, this is Mrs. Jackson. This is Chapter 3, Section 8, Part 1. In this last section, we're going to talk about more features of a polynomial graph, and specifically what we call the multiplicity of the zero. Before we get into the multiplicity, though, I want to take it back to the essential question of the entire unit, which is what can the graph tell us about the rules? Or in other words, what can the graph tell us about the function equation itself? And conversely, what can the equation tell us about the graph? So this last section is really going to put it all together to answer that essential question. One last note before we begin, just wanted to let you know that this topic is really Section 5 in the textbook, whereas I'm calling it Section 8. So if you want to read more about that, you can in Section 5. Okay, let's get started. We're going to focus specifically on the zeros or x-intercepts. And if you observe this particular graph, you'll notice that sometimes the graph passes straight through the x-intercept, while other times the graph may touch that horizontal axis and just kind of bounce off, kind of like a quadratic. And sometimes there's other features. For example, here, this particular intercept, the graph is kind of passing through it, but it's flattening out near the intercept. So that's even a different feature altogether. So if we take this one step at a time and zoom right in here on these x-intercepts, you'll see this is a pass-through. It appears that this x-intercept is at x equals -3. And if we were to write that as a factor in the function, then we would say x plus 3. And this is an example where we're just passing straight on through. It's on one quadrant, or top quadrant 2 there, going right down through quadrant 3. Here, it appears we have an x-intercept at x equals -1. Remember, that will result in x plus 1 factor. And this time it's passing through, it's going through all right, but it flattens out. So it's going through and flattening somehow. And then finally we have an intercept, or a 0 at x equals +2. That means that our factor would be x minus 2, and this is clearly a bounce off. It's completely changing direction. It's going down and now it's going up. Okay, so the key concept here, what is causing these different features at the x-intercepts, or these different attributes? The concept is called the multiplicity of 0, and what that means is how many times that x-intercept is repeated in the function. And another way to say that is the number of times that factor appears in factored form is called the zero's multiplicity. So we can use this information to look at the graph and try to piece together exactly what that function equation looks like. So if I start here on the farthest left of the function, I have an x-intercept equal -3, and we would write that as a factor of x plus 3. The multiplicity that causes the graph to go straight through, think linear, would be a multiplicity of 1. The multiplicity is the exponent, the number of times we would set that factor equal to 0 and solve. The next farthest left is x equals -1, which would be x plus 1 as a factor. And what causes this graph to kind of go through the x-axis but flatten out a little bit is another odd exponent, and it would be a 3. So we still pass through, but this higher degree here, or higher exponent, is causing the flattening. And then the final x-intercept we have is x equals +2. That would be a factor x minus 2. And you're probably already thinking, this looks very quadratic-like, and that's exactly right. the exponent that would be on that factor, or the multiplicity of that x-intercept, would be 2, and that's creating this bounce off. Now the only thing that we're missing in our function is this multiplier up front. What is the stretch, compression, and what is the sign of it? We can tell from the graph that we have an up. That means our degree is even. And we also know that A must be positive. However, to find the actual value of A, we would need a point on this function, a point that we can read right on the grid. So if we look at this, we have a y scale here of 5 per division. Even at a number as low as 5, it is difficult to see exactly where we're crossing the grid. So in order to truly determine A, I need to know definitively a point. So for now, we're just going to leave our function written as is. Okay, let's drill into the multiplicities a bit further. I'm going to start with multiplicities that are odd. And as we've already seen, the graph will pass through the x-axis if the multiplicity is odd. If we start out with the first odd number, which is a multiplicity of 1, as we've already seen, the graph will appear linear. And as the multiplicity increases, for example, 3, 5, 7, as that graph is approaching that x-intercept or that 0, it will become ever increasing flatter as the multiplicity increases. So we saw that a little bit with a multiplicity of 3 already. Let's take a look at how that would look with multiplicities even higher than 3. So this is clearly linear, and in the past we would think of this as y equals mx plus b, but in this case I'm going to ask you to think about this more in terms of factors. So in this case we have x equals positive 1 is our 0, and if we wrote that as a factor, that would look like x minus 1. And if we were to write that as a function, then we've got y equals x minus 1. We can see that we're passing straight through that x-intercept or that 0, so that's a multiplicity of 1. And indeed, if we connect that to our previous knowledge of y equals mx plus b, you can see that our slope is 1 and our y-intercept is negative 1 here. It's just another way to think of this as a factor. So we can see that our x-intercept is positive 1. It has a multiplicity of 1. And this particular graph is linear. Moving over, stepping up with the odd multiplicities, we can see here in our graph that we are passing through, again, at x equals positive 1, so our factor is going to be x minus 1. We see a flattening here, just slightly, so that is going to be x minus 1 with a multiplicity of 3. So our x equals 1 is our 0 with a multiplicity of 3. And if we were to do our distribution here on this factor, we can see that we have a cubic polynomial. And stepping up to the next odd number here, we've got more flattening. Again, our x-intercept is at positive 1, so that's a factor of x minus 1. And what's causing that increasing flattened appearance is a higher multiplicity. This case, it's a multiplicity of 5, so we have x equals 1 as an intercept with a multiplicity of 5. And we call this quintic. And finally, we've got even more flattening here. So I think you get the idea. Our factor remains x minus 1. This time we're stepping it up with a higher multiplicity of 7. And we haven't named this type of polynomial before, but it is called septic. Sept for 7. Okay, let's take a look at even multiplicities. And even multiplicities, as we've already seen, will appear as some kind of bounce off or changing of direction. It'll basically cause a turning point at the x-axis. So if we look at the lowest even number of 2, then the graph will appear quadratic, as we've already seen. And as that multiplicity increases to higher even numbers, 4, 6, 8, we're going to see a flattening at that bounce off, so it'll appear flatter. All right, so if we zoom in here on some evens, we see an x-intercept again at positive 1, which will give us an x minus 1 factor, and this is quadratic. Raised to a power of 2, so this is x equals 1, multiplicity of 2, and it's just a parent function, a quadratic, translated to the right 1 unit. Stepping up, we have here x equals positive 1 again, which is a factor of x minus 1. We see some flattening here in the graph, so we know that multiplicity is stepping up. So we have y equals x minus 1 raised to a power of 4. So we call that a multiplicity of 4. And a degree, if our first term is at a power of 4, we call that a quartic. And as we see even more flattening, again, we're at x equals, with my blue pen, x equals 1, which is a factor of x minus 1. We're seeing even more flattening here, so we're going to say that's at a power of 6 or a multiplicity of 6 on that 0. And we call a degree, a polynomial whose degree is 6, we call that sextic. And finally, really flat here, we've got x equals positive 1, factor of x minus 1. So I'm going to say that our x-intercept of 1 here has a multiplicity of 8. And a degree of 8 on a polynomial is exactly what you think it might be, what your intuition would tell you. It's octic. All right, so in this video, we talked about a key concept called zeros multiplicity, or the x-intercepts multiplicity. We looked at the effects that multiplicity has on the graph, specifically at those x-intercepts. We also looked at what the multiplicity looks like in the function equation itself. I hope this video helps. Thanks for listening.